What?
सर तपाईले लहरू पढाउनु हुँदै थियो सर थर्मोडाइनामिक्स को
Previously we started a thermodynamics. So previously we did the zeroth law of thermodynamics. Zeroth law. We said that when B, if A and B are in what? Thermal equilibrium or thermodynamic equilibrium, then what? A and B will also be in thermal equilibrium. That was the case. Clear? That was a zeroth law. So today we are going to learn about few of the things which you will need. And the parameters for there was two kind of system, that homogeneous and heterogeneous. We are considering a homogeneous system, or which is same everywhere. That is your homogeneous. So basically, on considering a homogeneous system, we had three parameters, which was pressure, volume, and temperature. These are the three parameters or observables or variables. Observables or variables in thermodynamics. Clear? So today we are going to do different forms of energy. What are the different forms of energy? One is, straight away you can tell about kinetic energy. Kinetic energy. Kinetic energy. Kinetic energy. You all know about kinetic energy.
Yes, sir.
Basically, it is the energy in motion. For in short, it's basically whenever a body starts moving, then it will acquire certain amount of kinetic energy. Energy in motion for a time being. I'm writing this as this thing. Now, second is your potential. You all know potential energy, which only depends on what your position. And third one, this is very important. We talk about internal energy. What is an internal energy? Any idea? Now, this is very important concept, and this you all should know. Internal energy. What does internal means? This is your intrinsic property of a given material. Basically, this is your sum of all the energy which the particle has. Clear? This is your sum of kinetic energy and potential energy. We can take consider this as an interaction between each and every molecules. So this is basically internal energy is your intrinsic property. Clear? Intrinsic property. Now, if you increase the temperature, what? The kinetic energy will increase. So that's why your what internal energy will start increasing. So this is your intrinsic property. Clear? Which is given by U, delta U. Delta U will take it positive when there is increase in internal energy. And negative when there is decrease in internal energy. That will be the convention which we will be using. And finally is your work done. What is work done? Now, internal energy is a different thing. This is an intrinsic property. Now, work done is slightly different. When you apply certain amount of external force, then what? A displacement or certain kind of motion will start happening. So the work done basically is a process by which the virtue of change occurs in any system. Now, basically the change in now the work done can be defined as what? Force into displacement, that you all know. Now the small work done you can write is as force into displacement. We are just using a one-dimensional. Now a body was sitting over here. Now it has been displaced by dx. Amount of force F was applied. Now the work done can be given by as force into dx. Similarly, this can be written in terms of thermodynamic variable. We can write as P into dV. Clear? P into dV. Now this is very important. Now in thermodynamics, the work done is given by P into dV. Clear? Is this point clear or not? Is it clear?
Yes, sir.
Now what is pressure? Pressure is force per unit area. Can we write in this manner? And volume is area into that small change in length. Can we write this in this manner? So area will cancel out. So will it be exactly this one? So can we write this as this one?
Yeah.
So now we will be able to write the work done in terms of your thermodynamic variable as this one. Now basically if you plot pressure versus volume, clear? If you plot pressure versus volume. Now if this is your linear plot, this for timing, let's consider this. This is the simplest. Now if you integrate this, what does integration means? Do you all remember? From 0 to, let's put this as V1. Integration basically gives you area under a curve.
Area.
Under the curve.
Yep.
Over here, the area is what? Basically this one. Can you see?
Yes, sir.
Yes, sir.
Basically, this is the area. So what will be the area of this? Directly, you can see from the plot itself what it will be. The length is V1 and this is P. Let's put this as P. So it will be half into base is how much? V1. Height is, how much is height? How much is height for this one? P.
P.
So this will be half V1 into P. So this is your work done. This is your work done. This can be written as a linear function. Now if you take integration of dW work done, then it will be pressure. Let's keep it as pressure is a linear function of V, as you can see. Can you see? So again, you will get exactly the same relation. Will be given by P into dV. Now you won't be able to get that, but you can see that P is what? Linear from 0 to P is basically V over here. When P is 0, V is also 0. When pressure is 1, it is also 1. When it is V1, it's again V1 or P. So P we can write as V. So V into dV from 0 to, we have to integrate from 0 to V1. So it will be how much? V1 squared divided by 2. And V1 we can write as, because P was P into V1 by 2. Now this is exactly the same thing. Now basically the area under the curve of P versus V will give you what? Will give you the total work done. Now this is slightly different. If you just remember, when you talked about, or when you started doing this work done, you always said that it was independent of path which it followed, because it only depends on initial and final condition. Do you all remember path independent? Do you all remember or not? The work done. Work done only depends on your displacement. Force into displacement. And displacement
Yes,
was
sir.
the shortest distance between two different points. Let's say you started. Let's consider our general work done. Now, let's say Deepika is sitting over here and she wants to go to point B. And she went all the way like this and she reached over here. Now, what was your total work done? The total work done is force into displacement. A was basically what? The shortest distance between these 2 points, which is BA.
BA.
Do you remember this? Because that is your
Yes, sir.
displacement. But over here is slightly different. Now, instead of being this as a linear function, if we had something like quadratic kind of form, then what it was? Suppose if we had this kind of point, quadratic function, and you reach exact same point of pressure. And now, can you see the area is smaller as compared to previous one? When you compare
Yes.
this and this, whose area is smaller? This or
Monica.
this?
Second one.
This has a smaller area, which means the work done is less over here. Work done is less over here. And work done is more over here. Now this is different as compared to what you have learned previously, which depend only on your initial and final position. Clear? When you take your pressure versus volume, it is, so that's why these are called your path dependent function. Work over here in your thermodynamics, this is a very important thing. Work done in your thermodynamics is mix is what? Path dependent. Now, do you understand what does path dependent means? Basically, it depends on which path you take from A to B. Now, if you start roaming all over the place, then what will happen over here? Now, if you take this another route, something like this. Now the area is larger, so that's why it's called what? Yeah, path dependent. Clear? Is this point clear?
Yes, sir.
Yes, sir.
So basically we learned about what? Your internal energy and your work. And work done, the most important point is your work done in thermodynamics is path dependent. This is very important. Now it depends on which path you take. And now depending on different path, what? You can define different process. Clear? One path for sure is one you can go in this manner. Can you go in this manner? Just write it over here. Let's choose different paths, okay? We want to go over here. Let's say we want to go over in this point. Let's say at this point. We want to go at this point. Now, what are the different paths which you all can take? One is straight line. You can always take a straight line. This is one path. This is pressure versus volume. Sorry, this is here pressure versus volume. And another path for sure is which one? You can take a straight line from here to here. Can you take this straight path? Another path is what? Directly you can take from here to here. Clear? And one is you can take like this. And another is path like this. Now actually, in short, there are infinite numbers of possibilities, but we will be only considering 4 of such kind. 4 of such kind. If you consider this line, can you see something is becoming constant? Let's consider this
Yes,
V1.
sir.
What is remaining constant? Volume is remaining constant.
Yes, sir.
And over here, pressure is remaining constant. And depending on this process are called isochoric, isobaric, certain things that we will do after this. So first, most important thing was their thermodynamic work done is what your path dependent. Clear?
Yes, sir.
Now, now there is another convention. How to consider that the work done is positive or negative? Whether it's a work done is on the system or by the system. Clear?
Yes, sir.
If the basically if there is an expansion of gas, or if there is an expansion of gas, now let's consider this equation. I think you are familiar, and I'll directly use that equation. Now dW you can write as P into dV, or W will be P into V2 minus V1. The volume has expanded. You have just integrated this from V1 to V2. I think this is clear. Let's write this as V final and V initial, so it will be easier for you to all know. Now over here, if VF is greater than VI, what it will be? It is said here W will be what? Positive. Yes or no? Now if second scenario is if VF is less than VI, then what will happen? W will be negative. Now depending on this process, what do you say? That this means this you can write as work done by the system. This is work done on the system. Clear? Why this is? I will just tell you. If VF is greater than VI, means if you started with a small volume VI, now it has expanded to what? To larger volume. Basically, this means it has expanded. Clear? So that's why the work done is by the system, because the system is trying to expand it. Now over here, you started with what? Larger, and you ended off with smaller. So now it's contracting. Now you are doing work on the system to contract it. So that's why what? This is said to be work done on the system. This you can think of the just as a piston. Just consider a piston or something. Just consider a piston. And you leave it like this. And there will be certain amount of pressure will be sitting over here. Then what? It will try to push it. Basically, it will start expanding. Now, can you see the work is done by the system? The work is done by the system. Now, in the second scenario, now you start pressing this. Now you start pressing this. Then what? You are contracting this. You are contracting this. Now you are doing work on the system to contract this. So that's why the work done is negative and is called work done on the system. Now is this point clear? Is this point clear?
Yes, sir.
So what are the thermodynamic variable or parameters? You all know. These are pressure, volume, and temperature. And equation of state, you all know. A relation between the values of all the three thermodynamic variables for the system is called here equation of state. Basically, the equation of state is, one example I will give you. When there is a certain relationship between all the thermodynamic variables, that is called here equation of state. Equation of state. That I will give you an example. For an ideal gas, you know, pressure into volume is equals to RT. Now, can you see there is a relation between all the thermodynamic quantities? This is called your equation of state. Yeah. And second thing, equilibrium. equilibrium. There are few types of thermodynamic equilibrium which you will come across. One is here thermal equilibrium, that is easiest. Thermal. What is here thermal equilibrium? What is a thermal equilibrium? When there is no more of flow of heat between two systems, that is called a thermal equilibrium. Clear? When there is no more flow of heat, no flow of heat, that is called a thermal equilibrium. And mechanical equilibrium, and there's also a chemical equilibrium. For time being, I think this is sufficient for you all. Thermal equilibrium. Now, part dependent and internal energy you have all understood. Now we are going to do here with your different kind of processes. Here, thermodynamic processes. Now, can you see your process was here? What here? Part dependent. So, depending on that part, we have what? Different what? Depending on that, we had what? Different paths, depending on that diagram of your PV diagram. So that's why now we are going to consider few of such. Just let me get that figure. Okay. Now, can you see this kind of processes over here? Now, depending on your path, now there are different processes. One is called a isobaric. What is the isobaric process? Now, can you see something is remaining constant over here? Let's make a table for this one. Are you able to see or not?
Yes, sir.
Let's start with this one. For a corresponding, we put V1, V2. This is V, this is pressure P. V3, V4. Let's consider this as V1, V2, V3, V4, so on and so forth. So what is the corresponding value at V1? That is exactly P. Let's write this as, this is at P. Corresponding value is P. For V2 also is exactly at the same point. For this also it's exactly there. Now can you see something is remaining constant over here? Your pressure is remaining, pressure is constant. In this kind of process, the pressure is constant. Wherever in a process, when your pressure is constant, it's called isobaric. Basically, baric or bar, isobars, do you all remember? Bars, they are barometers that measures pressure. So basically, isobaric means constant pressure. Constant pressure. Now there is here isochoric process. For a isochoric, what is remaining constant? Can you see something is remaining constant over here? Which value is remaining constant and which is changing?
So
Can you see?
is remaining constant.
Hmm?
And pressure is changing.
Pressure is changing, volume is remaining constant because it's the same volume all along. So this kind of process is called here isochoric. Isochoric process. See, and this is where your volume remains constant. Volume is constant. And there are two such processes. One is your isothermal and one is your adiabatic. What is your isothermal? Let's start with the simple one. What is isothermal? From the diagram, you won't be able to make it out. Which thing is remaining constant? But I will give you a better notion for that one. Don't worry. Isothermal basically means isolated. Thermal means what? Temperature is remaining constant. Constant. Clear? For isothermal, what is remaining constant? Isothermal process. What is remaining constant? Constant temperature. Temperature. Now, how did we get this kind of plot? That let's check. So let's start with your equation of your ideal gas. For an ideal gas equation, what do you get? PV is equals to RT. Clear? And can you see pressure T is constant? Let's consider T is constant. Then both of this RT is constant. Then RT divided by V. Now can you see that pressure is inversely proportional to volume when temperature is constant? Can you see or not?
Yes, sir.
Then what you will do? Now, then when you start plotting it, for a timing RT, I'm taking to be 1. Pressure, and we need some of the data. Let's start making data. V and corresponding. Let's start from 0. For 0, it will diverge. So that's why it has to start somewhere over here. So second one, let's put 1. Clear? Or half, let's put it half. Then P will be what? P will be 1 divided by 1 by 2. It will be 2. So the corresponding pressure will be 2. So for 1, it will be 1. For 2, it will be half. So when you start plotting these points, this is a very rough diagram, but still I think it will be sufficient to see. This is your volume, this is your pressure. This is your 0, half, 1, 3 by 2. I think we missed 3 by 2. But still it's fine. Let's put 2 over here. 3 by 2 will come over here. Basically, this is how much? Over here also, I think similar kind of half, 1, 3 by 2, 2. Now for the half, for 0, it was diverging. For half, how much you got? 2. So we have to start somewhere around here. So for 1, it's exactly 1. So it will come somewhere over here. For 3 by 2, we didn't do. For 2, it's somewhere around half over here. Clear? So when we plot this points, and we'll get something like this. So this is a process for your isothermal process. First, that's why for the isothermal process, you are getting a inverse curve like this. Now, is this point clear? Now, one more thing is left, that is adiabatic. Till now, do you have any questions? Any questions till now?
No, sir.
So now we'll take a break. Then after that, we'll start with the adiabatic process. Okay?
Yes, sir.
Okay, sir.
Now, if you have any question, you can ask me after this break.